So we can represent an electrical circuit just with something called a circuit diagram. Okay, and so let's look at the very simplest circuit that you could ever have, which is just a battery and a light bulb. So remember I said that the way that you represent a battery is like this, where this is the positive terminal and this is the negative terminal. Wires are just like straight lines, okay? And then resistors have this symbol here. Okay, so this is a resistor. So an example of a resistor would be a light bulb. Okay, so that's the simplest kind of circuit that you could construct with a battery and a single resistor. The battery produces something called an electromotive force, which is just a fancy way of saying voltage, right? The symbol for that is sort of like a swirly E. It's EMF, and it's the same as the voltage. Okay, so you could say that there's like a specific EMF across that battery, right? Like if it's a 9-volt battery, then that would be 0 volts. That would be at 9 volts, right? So remember, witers are equipotential lines. Equipotential. Or equipotential like surfaces. I mean, really lines because they're linear. Okay. So like if I have an EMF of like E, or 9 volts, then like what would be the potential there? 9. What would be the potential there? What would be the potential there? Okay, what would be the potential here on this side of the battery? 0, right? So this would be like 9, 9, 9. This would be 0, this would be 0, right? So what we could say is that there's a 9-volt drop of potential across that resistor, right? Because it's going from like right before the resistor, it's going from 9 volts. Right after the resistor, it's going to 0 volts because this wire is an equipotential line. Okay, so the circuit is going to the resistor is going to follow Ohm's law. Okay, so the current is equal to the change in potential over the resistor. So depending on the resistance of that resistor, remember the resistance is a function of both the material and the geometry. So depending on the resistance value of that resistor and the potential drop from like, you know, if it's a 9-volt battery from 9 to 0, we could calculate what the current flowing through that resistor is. Okay, what if you have 2 resistors and you connect them in series? Okay, so what that would look like, so here you've got a battery, same battery, let's say, wire, resistor 1, and then it's connected in series to resistor 2. So this is resistor 2. Okay, what does it mean for it to be connected in series? It means that the current flowing through both resistors is the same. Okay, so current, when you have series, the current is the same. Okay, so let's talk about, so let's say you have an EMF of E. Okay, so this point here would be at E, whatever it is. Okay, this would be at E, this would be at E. Okay, what about this point, halfway in between the 2 resistors? Like if I were to measure the potential here, what do you think that would be? No, just like more conceptually than that. So like this is the potential all along this surface is at, let's go back to the 9 volts. So 9 volts, right? And I know that the potential all along here is at 0 volts. What is going to be the potential halfway in between those two, assuming that R1 is equal to R2? The voltage is just going to be half, right? Or it's going to be like the E divided by 2. Okay? So when you're talking about a series circuit, the current is the same, and the change in potential across each of the resistive components in the circuit is equal to whatever the EMF of the battery is. So like the voltage drop across like resistor 1 plus the voltage drop across resistor 2 is equal to the EMF. Does that make sense? So current 1 is equal to current 2, and like assuming, well actually not even assuming, always, okay, when you're dealing with a series circuit, okay? What must be true about the potential difference across the two resistors? They have to be the same, okay? That's basically what this is saying. Okay, so let's say that we have two resistors. One of them is 5 ohms, and an ohm is just the unit of resistance. Okay, so this one is 5 ohms, and then this one is 10 ohms. Or sorry, 15 we said. In the questions, 15. And we want to know, like, what if I were to replace these two with one resistor, so with the equivalent resistor. So let's call this R equivalent. What would be the resistance of that equivalent resistor? When they're connected in series, it's like very intuitive. It's just the sum, right? So it would just be R1 plus R2, which is 20 ohms. Okay, so in series, you've got the same current. The voltages add. And the resistors add. Okay, and we'll pick up with the resistors in parallel next time. Okay, that's where we'll pick up next week. Okay? See you then. Okay, so we've got here this circuit on the right that has two resistors in parallel. And we want to know what must be true about the potential difference across these two resistors. So remember last class we talked about the fact that when you've got two resistors in series, you have to, the potential drops across each one of them, right? Such that the potential difference of two resistors in series adds to whatever the potential difference of the overall battery is. Okay, so how about in parallel? How would you answer this question? What must be true about the potential difference delta V across these resistors? Do they add like they do in series? No, right? So the potential difference is the same, right, across these two resistors. So it's the same. And not only is it the same, it's the same as the EMF of the battery, right? So like the drop in potential across resistor 1 is equal to the drop in potential across resistor 2 is equal to E. Right, so if this was a 9-volt battery, if this battery was 9 volts, you know that like this wire all the way along here, this is an equipotential, right? So the potential all the way along this line would be 9 volts, right? If everything along this line here would be 0 volts, right? And so here, between here and here, would be a change in potential of 9 volts. Same thing with between here and here, change in potential of 9 volts. Okay, so like from a current point of view, so we've got current going through here, going through here, going through here, right? Let's call that I total. what happens to the current at this point A? It splits, right? It splits into, say, I1 and I2. And then it comes back together here, right? So here, this would be I total again, right? And I mean, would the current through both of those branches necessarily be the same? No. What condition would have to apply for the current through those two branches to be the same? The resistors would have to be the same, right? So what must be true about the total current that flows through both resistors? The total current has to add, okay? So like while the voltage adds in a series situation, the current adds in a parallel situation, okay? It's like the exact opposite. So the total current would just be I1 plus I2, like the current going through one branch plus the current going through the other branch. Okay, so how would we find an expression for the equivalent resistance if we wanted to replace like these two resistors, if we wanted to replace them with a single resistor? So we want to like have the same exact circuit, but instead of having R1 and R2, we just have one resistor that has what we call an equivalent resistance, to R1 and R2. Well, so what we would do is we would start with I total. So we would say I total equals I1 plus I2. Oops. Right? And we know from last lecture, Ohm's law, right? The change in potential equals the current times the resistance, right? And so we know that so if we wanted to say like the change in potential of the equivalent, so like equivalent over the equivalent resistance, right? That's going to equal R. So like the whole voltage of the battery over the R equivalence, right? And then from there we can just sort of substitute things in. So VEQ over REQ equals the change in potential 1 over R1 plus the change in potential 2 over R2, right? And because these are the same, they cancel out, right? Because remember we're saying like the potential difference across the resistors is in parallel is always the same. So, so those cancel. So what you end up getting is the equivalent resistance is just this. Okay? So remember in series, the equivalent resistance, how did you find the equivalent resistance in series? You just added them together, okay? So here it's like the reciprocal of the sum. Does anyone have any questions on that? Okay. So the am I getting it? I think in the interest of time, let me just give you the answers, and then you can try these on your own because I think they're actually probably easier than the questions you've already seen that are like this. So unless I don't know how much did you actually see of this in the review / like other things you've done? Like you're okay with this? Okay. So let me just give you. So number 1, the answer is C. And number 2, the equivalent resistance is 20 ohms. Okay, so see if you can figure those out. This one in particular, the bonus, is like a good little puzzle to do. Maybe does someone want to just talk me through like the steps of how you would do the bonus? Like what would you do first? Does anyone want to give this a stab? Yeah, do you want to try it? Sorry? Oh, you're talking about one? No, the second one. Anyone have like an idea? Yeah, so where would you start? Which part of the, so you want to figure out what's in series, what's in parallel. Which part of the circuit would it make like sense in terms of simplicity to start? The left or the right? The right. I mean, in my opinion, right? So these three are in series with each other. So you just add them together, right? And you have an equivalent resistor that's like the sum of those three. And then you would say, okay, that, which turns out to be 88 ohms, would be in parallel with this one, right? So then you could add it in parallel to that one, and then you end up just with like, you end up with something that looks like this. So step one is like add these three in series. Step two would be like add the two resistors on the far right, like in parallel. So that would be like these three plus this one, right? And then step three would be you'd have this thing that would look like this. Let me see if I can draw it. And I think this is the only really like tricky part. Oh, that turned into a circle weirdly. Okay, so right, so you have this thing that looks like this, and this is going back to A, and this is B here. Okay, so, and this just, I mean, if you want to check your work later, that's 7, this is 24, this is 14, and this is 36. So what is this? How would you reduce this down? Like, what would step 3 be? Yeah, you would add them up, right? So like these two are in series, and these two are in series, but they're in parallel to each other. Do you see that? So you'd have like as a final equation, you'd have 1 over REQ equals 1 over 31 plus 1 over 50, and then when you reduce that down, it solves to 20 ohms. So see, like this would be a good one to practice.